Welcome to The Explainer. Today we are taking a completely objective, really deep dive into what's arguably one of the most polarizing but absolutely fascinating subjects of our time. We're talking about nuclear energy. We're going to break down the whole shebang, the pros, the cons, the massive potential, and of course, the very real danger zones of atomic power. So, here's the big question right off the bat. As the world pushes desperately for clean energy, is nuclear power our carbon-free salvation? Or is our absolute greatest liability just waiting to trigger a catastrophe? Well, let's look at the reality of how atomic energy is actually helpful for us, and exactly where it falls short.
All right, here's our roadmap for today. We'll be looking at the power of the atom, unmatched energy and reliability, the high cost of power, a history of meltdowns, the invisible cyber threat, and finally, weighing the nuclear future. Let's get right into it.
Section 1. The power of the atom. Now, before we get into global disasters or massive power grids, we kind of need to strip away all that sci-fi mystique. Ultimately, it all comes down to nuclear fission. And despite the insanely complex engineering of a modern power plant, the core concept here is surprisingly straightforward. Fission is literally just the process of splitting fuel atoms, usually uranium-235, in a highly controlled chain reaction. And doing this releases just massive amounts of heat. So, think of it like a microscopic game of billiards. Neutrons collide with uranium atoms, splitting them apart, which then releases even more neutrons to keep that chain going. But the real heroes here are the control rods, which you can see illustrated beautifully in these vibrant diagrams. These rods are often made of boron or cadmium, and they're lowered right into the reactor to absorb those extra neutrons. That is absolutely crucial, because it keeps this intensely hot, energetic reaction from spiraling completely out of control. And honestly, what's incredibly fascinating is how beautifully mundane the next phase actually is. Once we have that intense atomic heat, the mechanical steps are, well, surprisingly traditional. Step 1, the fission heats up the water. Step 2, that water turns into highly pressurized steam. Step 3, the steam rushes through and drives a massive turbine. And finally, Step 4, that spinning turbine turns a generator to actually produce the electricity that powers our homes. So when you think about it, it's essentially cutting-edge atomic physics powering a really sophisticated steam engine. Crazy, right? Section 2. Unmatched energy and reliability. So, when we look at why grid operators value this tech so incredibly highly, it basically comes down to this astonishing figure right here, 93%. In the United States, nuclear power plants achieve a 93% capacity factor. That means they're up and running at full capacity over 93% of the time. To put that into perspective for you, they are nearly 3 times more reliable than wind or solar power. Unlike renewables that, fluctuate with the weather, nuclear provides this rock-solid, steady baseload of power that we can just count on 24/7. And the efficiency, it's just mind-boggling. A single uranium-235 fuel pellet, literally the size of your fingertip, packs the exact same amount of energy as 1 full ton of coal, or if you prefer, 149 gallons of oil. It delivers an unimaginable amount of zero-emission energy in this tiny little package. This is exactly how atomic energy is so immensely helpful for us. It provides massive amounts of steady power without that immediate carbon footprint you get from fossil fuels. It's a real game changer. Section 3. The high cost of power. But of course, there's always a catch, right? These benefits come with some severe logistical hurdles, bringing us to the cons, namely this immense disparity in lifespans. Now, yes, a nuclear reactor operates for a really long time. They routinely receive license extensions to generate all that carbon-free electricity for 60 to 80 years. But here's the kicker. The radioactive waste, which is full of plutonium and other hazardous materials, remains dangerous for thousands of years. So we get decades of clean power, sure, but we're leaving behind millennia of highly dangerous waste that requires incredibly durable and frankly very expensive engineering to safely manage and contain. And then there are the upfront financial realities, which are quite frankly staggering. Let's look at the Vogtle nuclear plant expansion in Georgia. It was originally budgeted at around $14 billion. The final cost? Over $30 billion. Plus, construction was delayed from 2016 all the way out to 2023 and 2024. These massive financial risks and long delays heavily limit global development. It's pushing a lot of utility companies toward much cheaper, lower-risk investments like natural gas or solar power.
Section 4. A history of meltdowns. Now we enter the danger zones. We have to look objectively at the devastating physical consequences of what happens when this highly complex tech fails. Because while major accidents are rare, when they do happen, the impacts are catastrophic. Walking chronologically through this grim timeline, we see the 1957 Windscale fire in the UK, and then the 1979 Three Mile Island meltdown in the US. Then in 1986, the Chernobyl disaster forced 220,000 people to relocate. And of course, in 2011, a tsunami triggered the infamous Fukushima meltdown. But I want you to consider 1961 for a second. The SL-1 steam explosion in Idaho. This was caused by a tragic human error. Workers were supposed to lift a central control rod just 4 inches. Instead, they lifted it 20 inches. In literally less than a second, power surged 6,000 times above normal, vaporizing the fuel and causing a lethal steam explosion. It just goes to show exactly how razor-thin that margin for error really is.
Section 5. The invisible cyber threat. Okay, so here's the thing about modern danger zones. Today, a plant doesn't necessarily need a massive tsunami or a physical operator slip-up to face a meltdown. According to a report from George Washington University, nuclear facilities have some pretty severe digital vulnerabilities. Because these plants have to operate 24/7, they often use unpatched, off-the-shelf software. Their critical SCADA control systems sometimes rely on inherently vulnerable TCP/IP networks. And then there's the whole bring-your-own-device threat. I mean, imagine a contractor bringing a malware-infected laptop into a highly sensitive area. That alone could theoretically infect the entire facility. And it's not just theory. We've already seen sophisticated malware like Stuxnet that was specifically designed to sabotage nuclear infrastructure. To really drive home the reality of our current digital defenses, experts offer this pretty chilling assessment. The nuclear industry is not investing as much as they should be in cybersecurity. Operating on this whole security through obscurity mindset? Yeah, that's just no longer enough, especially when the attacking logic of malware is practically publicly available online. Make no mistake, the physical consequences of a successful cyber attack could be completely identical to a physical meltdown.
Section 6. Weighing the nuclear future.
So, knowing all these immense benefits and the genuinely terrifying risks, what comes next? Well, the proposed solution by a lot of folks in the industry is the Small Modular Reactor, or SMR. These are designed to be smaller, theoretically safer, and a lot easier to build. But hold your horses, because they still face 4 massive hurdles before they can take off. First up, technology risks. We just don't have the operational experience yet to actually prove they work as expected. Second, market risks. Supply chains could easily fail, or prices might remain completely uncompetitive. Third, political appetites. Public support for nuclear can literally vanish overnight. We've seen it happen in places like Germany and Japan. And fourth, the regulatory pathways are just completely undefined for this kind of new tech right now.
As we wrap up, I want to leave you with this somewhat provocative thought. You've seen the incredible pros, the 93% reliability, and those tiny fingertip-sized pellets replacing literal tons of coal. It's amazing. But you've also seen the staggering $30 billion price tags, the millennia of highly radioactive waste, the devastating historical meltdowns, and those looming invisible cyber threats. So what do you think? Can humanity safely manage this immense carbon-free power, or are the physical and digital risks simply way too vast to control? Thank you so much for joining me on this explainer today, and as always, keep learning.